is go through 715, 716, and then show you, because the Z transform, it parallels with the DTFT, almost identical, except instead of e to the j omega, you have a Z. That's basically the only difference. So today what I'm going to do is, I'm going to mention a few things, but I want to continue on with the thoughts on Z transforms and go through 715 completely, and I'm going to add a few things too to some of these problems. For this one, this is 715A. For starters, it's just simply if I gave you x of n equal to u of n plus 2 to the n u of n, and you were asked to do the Z transform of this should be an automatic, in my opinion, because these are two of the most basic forms. I'll just put them up here. I'm trying to put this side with the standard Z transform pairs. You should know. If you have u to the n, that goes to just z over z minus 1. If you have a to the n, u of n, that goes to simply z over z minus a. Now, the one difference that's important to understand, well, the one thing you need to add anytime you do a Z transform is the region of convergence. And I'll put that over here. So what is the region of convergence for this one? Now just look at that right there and think about u of n. U of n times z to the minus n, right? Sum from 0 to infinity is the value of the Z transform, right? But what do you need z to be in order for this thing to converge?
Greater than 1.
That's right, magnitude of z greater than 1. And so for the region convergence here is magnitude of z greater than 1. For this one, it would be in general class?
Greater than A.
Magnitude of z greater than a. And a could be 3, it could be 2, it could be minus 1, or it could be 1 plus j. It could be complex. A is not limited to be real or imaginary, positive or negative. But the region of convergence requires that z is greater than a. And this is for things like stability in the future. Now, these two are necessary that you know. Another one you should know, if you have n u of n, well, we know u of n goes to z over z minus 1, right? To get this one, you could say if you take minus z, there would be a minus z times the derivative with respect to z of the quantity z over z minus 1. I'm using the property I specified. Do you all recall that? N times u of n? I'm going to remember that. All right, it's in the properties. If you don't, it's if you have n times any x of n, and you know x of n goes to x of z, you simply put minus z in front of that, take a derivative with respect to z of x of z. Do you remember doing this type of thing for Laplace? Do you remember anytime you had like t times u of t? If you wanted to find out what the Laplace transform of that would be, well, the Laplace transform of u of t was 1 over s, right? And therefore, you would take the derivative of 1 over s, put a minus sign in front, right? And then multiply by s. Do you all recall that, class? How many do for Laplace? It's the same thing here. This is one you should know, and this actually becomes n times u of n here. Simply goes to z over z minus 1 squared. I believe he has this one in his table, actually. I'm not sure. All right. So I just want to put some tablet with this. For this one, this is a straightforward one. This would give me x of z if I went this way. For u of n is just z over z minus 1. And the second part here is plus. And here you're going to have z over z minus 2. Now, they ask you to get really just a single fraction where you have a numerator and a denominator. Now, they do that for a lot of reasons. One of them is for synthesis, and others for stability. And if you look at this, this itself would be equal to what? Well, it would be equal to z times z minus 2 plus z times z minus 1 all over z minus 1 times z minus 2. Do you all agree with me there? Class?
Yes.
I just got a common denominator, correct? Now you can keep fooling with this thing and you can see that this becomes, well, I have z squared, so I have 2z squared right there. And then I have minus 2z, and I have minus 1z or minus 3z all over, and if you want it would be z squared, right? And then it's going to be minus 3z plus 2. And that would be a fraction. That would be the transform of that. If you want it in terms of a numerator and denominator. Now he asked for rational fractions. Getting irrational expressions for this problem. So that would be the first part, part A. Part A. Part B of the problem says, this is straightforward. He has x of n equal 2 to the n u of n plus 3 to the n u of n. This is almost boring. For this one, it's really a to the n u of n in both cases, right? So I'm just going to put it down. This will become, in a straightforward way, simply z over z minus 2. And it's going to be plus z over z minus 3. Out of curiosity, what's the region of convergence for this one? What?
Z, magnitude of z greater than 3.
Greater than 3. It's always the, this one, z over z minus 2, magnitude of z greater than 2. But because you have a second term there, it's always going to be the value of z, the largest value of z in magnitude. So the region of convergence for this one is magnitude of z greater than 3. And this is more for stability than anything. After that, the next one I want to make sure, I'm trying to cover as many different forms of functions that you have to be aware of to get the z transform. The next one he gives, and I'll put it right under here for part C, he uses these brackets, curly brackets, and he puts, 1 minus 2, right? And then he has plus 2 to the n u of n. And this is the x of n. So now I'm going to say some, isn't that the function your book has? Right? So for this one, if I have 2, oh, he did this too. That, what does that indicate?
Starts at 0.
That's where n equals 0, right? So n equals 0 and 1 are the values of n, and these are the values of the function. All other values are assumed 0. Understand, everyone, class? So when you look at this, I should mention something, because here it's good doing a problem when it exposes some information, some either property or transform pairing that is used over and over again. In general, for z transforms, if you have anything with curly brackets where you have a0, a1, a2, dot, 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 a to the n here. And this is how x is going to be defined, and I'm going to put the 0 right there. Now, by the definition of the z transform that I'll put over here, I know that x of z, the definition, is equal to a summation r start at 0 to technically infinity of x of n times z to the minus n, right? Now that's the definition. If there's a finite number of terms, think about this. X of 0 times z to the 0 is just x of 0, correct, class? The next term would be x of 1 times z to the minus 1, or simply divided by z, right? The next term after that is x2 divided by z squared, and so forth. So you can, if you have this series, just by inspection, you can get the z transform of it by taking, it would be a0 plus a1 over z plus a2 over z squared plus dot, dot, dot. And it's going to be plus a to the n over z to the n minus 1. And that's the general form. How many see this right here? Follow me? Now get back to this. The first part, right here. For this one, I'm about out of space, but if we take a look at this, well, this is going to be just 1 divided by z to the 0 over 1, right? Then it's minus, God say it, minus 2 divided by z, right? That's the first part. That's the z transform of that, right? Does everybody understand that? What about this one?
It's just z over z minus 2.
Right, over z minus 2. Now that is a legitimate function right there. They want them in terms of a polynomial. And the easy way to do that is you can see the polynomial here would be z, I mean the common denominator would be z over z minus 2, right? So you have z times z minus 2 here. The first one you have to have the whole thing, z times z minus 2, because that's 1 there, right? The next one you're going to have minus 2, and you're going to have times z minus 2, and then finally plus z times z itself, or plus z squared. And that would be, you can collect terms there. You've got z squared, z squared, so you have 2z squared minus 2z or plus 4z, so it would be z squared plus 2z on top. Do you agree, class? How many see what I'm up to here? Follow me? I'm just going through this to make sure that any form doesn't scare you. If you see curly brackets, anything like that. Got a few other things to mention too. Yes, sir?
On that x of z that you have under the curly brackets to your right.
Hold on. Where? Here?
Right there. Yeah. On that last term, why does it end at z to the n minus 1?
Well, think about this. This is, tell you what, if this is z to the 0, this is z to the 1, you're right, I can leave it as z to the n, z divided by n, yes. And really what I'm telling you, it's progressive. The first term, if this is the 0, by the way, that's assuming that's the 0, that's divided by z to the 0, z1, z squared, and so forth. That's the thing about this. I'm not trying to spend too much time in different obvious forms. But are you okay with that?
Yeah.
All right, now, one other thing, and this pops up. People oftentimes don't catch this. What if I want the z transform of, I'm going to continue on this problem, but let me erase these right here. There's no NCAA games on today, are there? I didn't think so. All right. Now, what if I had this function? Suppose I have something where I have z over z plus a, not minus a. How do I deal with that? Anyone? I want what? Z over z minus something, don't I, class? Follow me? So what I would do is say this one is actually equal to z over z minus a minus a. And then minus a is, quote, my old a. Does that make sense? Now the inverse the inverse transform of this going the other way, the thing that rendered that would be minus a to the n u of n. Does everybody follow me on that? I'm making sure you see this because I know for a fact if I put down something I have z over z plus 4, that factors like this, people will wonder what to do with that 4 because it's not negative. That's how you make it negative. By the same token, that could be z over z, and it could be like 10 at an angle of 40 degrees. Do you follow me on this? Let me just put it down so you can see it one time. Suppose I have z over z plus quantity 10 e to the j, make it pi over 3. Make it that way. Now what do you do here? The form we know is z over z minus something, right? So we make it that. Now we say that's actually z over z minus the quantity minus 10 e to the j pi over 3. There's other ways to do this. I'm going to just make a negative sign in there. Understand, class? Give me a show of hands if you follow me. Now what's this going to be?
Negative 10.
Now it's going to be what? Minus 10 e to the j pi over 3 to the nth u of n. Is everybody with me on that? I'm just trying to make sure all the forms are beaten out. Something else that happens, and this is a property that I talked about last time. Do you remember that if you had if I had this form, a to the n u of n goes to z over z minus a, right? I went down and I showed you that, well, better yet, let me just do it. If I had x to the n times u of n, if it went to x of z, then x of n minus 1 u of n, now remember this is u of n, right there, that actually goes to what? That went to x of z, right, divided by z, plus x of minus 1. Do you all remember that, class? Isn't that right? I mean, but because this is a u of n here, right? I mean, how many remember this? Give me a show of hands. Now, depending on what x of n is, but if x of n is 0 for all negative values, you can get rid of this. Are you with me on that, class? And a nice way to think about it, if you have x of n minus anything a times u of n minus a, that will transform, this is the most common form, x of z over z to the a. Remember that. Now, does anybody have your book with the properties open? Do you see what I'm showing you there? That property? X of n times u of n minus a? Or they might have n minus a different symbol. Which property is it?
They have x of n minus m.
Oh, m. They use n minus m. Well, I'm going to use a there. Follow me on this, class? This is important what I'm showing you. Now, something that I'm going to say that occurs all the time is we're going to have something like this. We'll have forms that have some 1 over z minus a. All right? Well, what does that look like? It's almost right, isn't it? I know if it was z over z minus a, that would have come from a to the n u of n. And that looks like x of n, right? Are you with me, class? Now, if all of a sudden I have x of n minus 1, that's like a to the n minus 1, u of n minus 1, right? And it's like taking that function right there and dividing it by z. Or getting rid of the z on top. How do you see this? So therefore I can say that a to the n minus 1, u of n minus 1, simply goes to 1 over z minus a. Are you with me? And one of the things that happens whenever you have delays, singular delays, if it's 1 or delays by some number, what will always happen is the general form of the transform, the inverse transform, like a to the n times u of n, will be delayed by that. The number of, you might could say, the number of times it's divided by z from the standard form, z over z minus a. I'm not completely accurate, I'm not getting an exact description of what I'm trying to say, but I'll show you a lot of this stuff. Okay, I think I did through C, didn't I, class? I mean, if you've got your if you did your homework, if you've got your book, what's part B of that one? I don't want to keep carrying that tablet around. Anyone?
2n plus, or 2 to the n plus 1.
All right, here x of n is equal to 2 to the quantity n plus 1. Go ahead.
Cosine of 3n plus 4.
3n plus 4, u of n?
Yes, sir.
Lots of ways to do this. Lots of ways. I'll show you. I covered modulation, didn't I, last time? Right? The problem with this one is this has an angle built in. It's not just omega naught n. Here, I've got an angle built in. I'll show you the easiest way to do this, in my opinion. First, I work with the 2 to the n plus 1 times u of n. And I say that that's really equal to 2 times 2 to the n u of n. Does everybody grant me that? That would be 2 to the n plus 1 is 2 times 2 to the n. Isn't it, class? So it just puts a scale factor out there. And this one's a nice, easy transform that I know. Now I go ahead and I take this cosine and I use Euler's identity on it. And in doing so here, I'm going to go ahead, I'm just going to say this is really times the cosine of 3n plus 4. But now I'm going to go ahead and use Euler's, and I'll say that x of n here, please watch this, that's going to be 2 times 2 to the n, and then it's times e to the j 3n times e to the j 4 over 2. That's the first term in Euler's identity, right? It's e to the j theta divided by 2 plus e to the minus j theta divided by 2, correct, class? And I just multiplied it by the 2 times 2 to the n u of n. So there's going to be a u of n here, plus, and then it's 2 times 2 to the n times e to the minus j 3n times e to the minus j 4. That's this, divided by 2. Can everybody follow? How many see what I've done there with Euler's identity? Give me a show of hands here. Who does not? If you don't be afraid of showing it. Euler's identity is this. Please make sure. For cosine of theta, it's equal to e to the j theta plus e to the minus j theta divided by 2. You have to know that. Where theta is whatever the argument is of the cosine. In our case, it's 3n plus 4. Yep.
Why is the u of n only the first?
Because I forgot it. Thank you. Thank you. All right, now, hear me on this. Can everybody see that this 2 and this 2 cancel? So I'm going to just get rid of both. Okay? The next step is collecting everything with a coefficient times something to the nth power times u of n. That way I fit my form. Understand, everyone? So what is this going to be? That's going to be x of n here would be equal to, notice that the e to the j 3n and 2 to the n are the only things with arguments of n that are powers besides u of n. So I can take the e to the j 4 and leave it out in front. That's like a constant. All right? Never changes value. Then I put the argument 2 times e to the j 3 here, and I put it to the n power times u of n over here, and I'll stop for a second. I take e to the minus j 4 here, and then I take 2 here times e to the minus j 3 here to the nth power u of n. Please take a look at that. Make sure you see what I've done. I'm just showing you the easiest way. Whenever you're given cosines and sines, if you're not sure of the exact transform, the easiest thing to do is represent them as Euler in their Euler identities. Then it becomes easy. Does everybody follow? Now, what does this form actually look like that I have here? This is nothing more than a scalar value. They do not change versus n. They simply come down and multiply the z transform. Does everybody understand that? The next thing is I have something to the nth power times u of n. That's like a to the n u of n. Do you follow me? Therefore, this transform becomes my x of z equals to e to the j4. And now it's going to be times z over, in this case, I'm sorry, yeah, z over z minus 2 e to the j3 over here plus e to the minus j4 over times z over z minus 2 e to the minus j3. Now that's the z transform. That's accurate and it's exact. You can get this in the form of a cosine. I should say you could get it in trigonometric forms if you want in terms of a cosine or a sine, cosine and sine representation, by getting a common denominator. Now if you multiply this times this, and then up here you multiply it by this, and over here you multiply it by this, and you start grouping terms, you can form cosine and sine operators in there. But what I'm showing you here is the essence. It's correct. You follow me? In the book, I don't know if he has this in the table. Doesn't he? He has a to the n times cosine of theta n plus some angle, and it goes to like a z squared minus 2az times the cosine of theta minus another term all over z squared minus 2az cosine of theta plus a squared. Does anybody remember that at all? It's in the book. It's just a lot of, more or less grouping terms. You don't remember it. It's understandable because you haven't worked with it long enough, but you will. You work with these things long enough, you can't help but memorize it. I mean, it's the way to actually, I believe this with all my heart. Worst thing you can do is flashcards. I know people do it. You want to memorize something? Have to use it to solve problems over and over again. that thing will be burned in your memory. You can't forget it, even if you try. I'll just tell you. So is that the last one there? All right. Now I want to go through the next problem. I didn't give you this, but this is going to be problem 716, and I want to work that too. All right. Can somebody tell me 716? The first part. I don't have that. Which is the first part of 716?
N U of N.
All right. They want x of n is equal to n times u of n. Now this is really a property. First, I'm going to say I know that u of n goes to z over z minus 1. That you have to know, right? Now, if I think of this as call it x1 of n here, then if I have n times x1 of n, and call this x1 of z, I know that that will go to minus z times the derivative with respect to z of z over z minus 1. I thought last time I showed the proof of how that n times x of n goes to minus z over the property times the derivative of z, x of z with respect to z. Did I do that or not? Anyone? You don't remember? Here's how this happens. Look at the definition of the z transform. It says x of z here is a summation from n equals 0 to infinity of x of n times z to the minus n. First, establish that in your head. You have to know that. Right? Now take a derivative with respect to z of both sides. The reason I'm taking a derivative with respect to z is I want that minus n to pop out in front. I want the form here to be nx of n. Does everybody see that? So I take one derivative. And when I do that, I get, now that minus n comes out. Now I get a summation from n equals 0 to infinity of minus n times x of n, z to the minus n, but it's actually going to be times z to the minus 1. Right, really, isn't it z to the minus n plus 1 plus? Follow me on that? So I broke out the minus 1 by itself. Does everybody see this? Give me a show of hands. This is straightforward, but you have to make sure you're clearly thinking. See, now if I have that, I'm getting there. I have my nx of n, don't I? Now if I multiply by a minus sign, I get rid of there, right? And then if I multiply by z, I get rid of this. And what is that? The remainder is, that is the definition of the z transform of nx of n, isn't it, class? That's why it's minus z times the derivative with respect to z of x of z. Now, what does that bring us to? Well, for this one, it would be minus z, right? And then I would have the derivative of the first z is 1 over z minus 1. So it's 1 over z minus 1. And then it's going to be z plus z times the derivative of z minus 1, which is z minus 1 to the minus 1 power. And it's really going to be minus z over z minus 1 squared. So really I'll put the minus here. And now to get a common denominator would be z minus 1. So I make this z minus 1 squared, z minus 1 here. And now group terms, and you can see what happens. Z minus z goes away. I basically have minus 1 times minus is plus 1 over z, or this becomes z over z minus 1 squared. This is one you should know. I should commit to memory. This is going to be nu of n. And if it was a to the nu of n times, or n times a to the nu of n, this would be an a there. Okay? Everybody with me on this? All right, that was part A. What was part B of that problem?
-1 to the n.
Oh, wait for 1 second. Oh, this is, Yeah, we've covered that part, but next part is going to be x of n is -1 to the n. Go ahead.
3 to the negative n.
What?
3 to the negative n.
All right. Go ahead.
And then u of n.
All right. Now what this is doing is exposing you to forms that you have to think about, so you don't feel rattled when you see them. Now always think about one thing. You would love to get something like that, where you have a constant to the single power n. Do you understand that, class? When I look at this, I see I could have -1 divided by 3 to the nth power u of n, and that would be identical, would it not, class? Here's what people try doing. They make it real hard. They're going to say I have something a to the n times u of n. I get the transform of that, and then I use the property of x of n times a to the n, gives me another transform. Don't do that. Just lump it together into a single constant. Understand, everybody? Now, what is this going to be? The z transforms. This is x of n. Just by inspection, what is it? Z over z minus -1/3 or z over z plus 1/3. Correct, class? Either form. Is everybody good with this so far? What's the next one?
U of n minus u of n minus.
Ah, this is a good one. I see people. Well, I asked for information about this, and sometimes people struggle. I'm going to show you a couple ways to do this. I guess this is part C of that problem. Here, they have x of n equal u of n minus u of n minus 2. Do you all agree that u of n has values that are non-zero only for n greater than or equal to 0, right? U of -1 is 0, -2, and so forth, right? That's important we establish that. One thing I can say, therefore, because of that, I can say the transform of this, when it goes, now I'm just going to use the transform properties, I mean the actual pairings, u of n goes to z over z minus 1. Do you agree with that? Now the second one, remember, all the values, I didn't put that property up here. Yeah, I did. All the values of u of n are 0 for n less than 0. That's my point. So that means this one goes to z over z minus 1, same as u of n, but now I divide it by z to the power, right there, 2, because it's delayed by 2. Do you follow me on that? So now you divide this by 1 over z squared. Just watch. Do you all follow me what I'm doing here? Give me a show of hands. Does he have this one in the book, by the way, u of n minus 2 or u of n minus 1? He might have a to the n. See, he should have that one. All right. Now, when I look at this, do you all realize I can factor out z over z minus 1, and I can get 1 minus z squared, or minus, sorry, 1 minus 1 over z squared. Do you all agree with that? Please just take a look. I'm not trying to race through here. I just want to hit the high points. Now, this I don't like, the 1 over z squared. I want everything to have a power of like a constant or z to the n power, not z to the minus power. Follow me? So now I'm going to multiply top and bottom by z squared. Understand? So when I multiply this top by z squared, right, that's the numerator, right, I get this equal to z squared here. And this becomes minus 1, just listen to me. And down here, when I multiply by z squared, right, downstairs, I get 1 over z squared here, right? Class? Now what happens here? Well, do you all see that this z squared and this z can be factor 1 out, right? It's 1 over z. Z over z squared is 1 over z. How many see that? All right? Do you all see it? So I'm going to just do that. Leave that 1 over z. Now when I have z minus 1, that's really, or z squared minus 1, that's z minus 1 times z plus 1, isn't it? Think about that. That can be factored. Let me put this over here. This is going to be 1 over z times z minus 1 over 1, and really I can get rid of that. And this is going to be z minus 1, z plus 1, if you take a look. Do you all agree with me there? Just factor z squared minus 1. Z minus 1, z plus 1. Agreed? What do you see happening next? And now I get this. I get z plus 1 over z. Now that's correct. But I'm going to show you an easier, and by the way, what would be another way to write this? 1 plus z to the minus 1. Correct, class? Now, the easy way to do this one, if you wanted to do it real fast, is this. Just think about the values that are non-zero. What is this function at n equals minus 1?
0.
When n equals 0?
1.
When n equals 2?
1.
I mean, when n equals 0, it's 1. N equal 1, it's 1, right? N equal 2, it's
0.
0. So I can write this as curly bracket form. I can say this is 1, 1, and just put the bar right there, because that would be n equals 0. Isn't that right, class? How many see this is the same exact thing?
Yeah.
Just do it. N equals minus 1, it's 0. N equals 0, it's 1. N equal 1, it's 1. N equal 2, it's 0. After that point, it's always 0. So I can write that as just 1 and 1. Well, I know that's going to be 1 plus what? 1 over z, right? Just like in that property I showed earlier. How many remember that?
Yeah.
Do you guys get this, follow me on this one? I'm just using the thing where I said if you have a finite number of terms, just start dividing by 1 over z to the n, right? First term, n is 0, so it's just itself. Second term is a 1 divided by z. Third term is a 2 by z squared, and so forth. Now this is quick to do. One look, you got it. You don't need to fuss around in any of the forms, right? This is right, what I've showed you here. That's right, it's right here. But I'm going to tell you, it's a lot easier to deal with this if you're doing some sort of manipulation of an h of z than it is with this, or this. Yes, sir?
Can you explain how you got from the u of n minus u of n minus 2 to the 1, 1 again?
Sure. All right. U of n is 1 for n equals 0 on up, right? U of n minus 2 is 1 for n equal 2 on up, right? Well, for values of n less than 0, this is 0 necessarily, right? All right. When u of n equals 0, this one has not yet come on, and this one has. When n equals 1, this one's still on, and this one hasn't turned on yet. And then when n equals 2, this one's on and this one's on, they cancel. That's all. It's just a mathematical representation of really two non-zero values. Go ahead.
I think I might have missed it when you had did it, but like right under x of z, where it said 1 over z times 1 over z minus 1 times z squared minus 1. How did we get to that?
All right, first, this corresponds to this, and this corresponds to this. Have you got both of those? Now I factored z over z minus 1 out front of both of these. So that's this. All right?
Okay.
So I have 1 minus z squared. 1 minus 1 over z, pardon me, squared. Follow me? Then I multiply top and bottom by z squared. So I had z squared minus 1 here, and I had z squared down here, and there was a z here, so I had z squared by z is just, z squared into z is just 1 over z. How many follow me on what I did here? Take a look at your notes. It should, if you do this, when I come from this point and I factor z minus 1 out, z over z minus 1, I get 1 minus 1 over z squared. Then I multiply numerator and denominator by z squared, and then you're left with basically that. And then I factored z squared minus 1. That's it. Yes, sir? Nobody? No other questions? All right. That's that one. What's the next one? That's it? Okay, good. Now, and I'll tell you, there's a lot of ways to get the z transform from properties. You don't have to follow my way. Right? There's several different you can use a variety of properties all the time to get it, just like with Laplace. You could use different properties to do different things. You didn't have to use modulation. All right? You could do it different ways. Okay, I want to mention two forms that you keep. You're going to see these things over and over again, so I'm going to put them up here and you should know them. And they more or less take care of just about every. This transform pair that I'm going to show you, I think we proved it, but the thing about this, it occurs so many times, just realize you're going to need to know it. You don't have to prove it every time or develop it, but I'll show it to you. And this is like the most common type of Z-transform pairing you need to know. Now, this stuff that I've showed you here, I didn't put the delta function in here, but I think you know what the delta function is, right? Delta of n goes to 1, delta of n minus n naught goes to simply z to the minus n naught. And we could spend more time with a series of delta functions, but it really doesn't give you much information. What I want to show you is this. In general, a couple of the functions that you run into over and over again are this. You run into a to the n times cosine of some omega naught n times u of n. And you run into a to the n times sine of omega naught n u to the n. Now earlier today I did this one, only had cosine of theta naught n plus some offset, plus an angle, right? I don't worry about that. If I see that, I'll just do what I did before and use Euler's. But for these two, I know this one will always render downstairs. It'll be, if you look there, it's going to be z squared minus 2az times the cosine of the angle, theta naught, and it's going to be plus a squared. And on top here, it's going to be z squared minus 2, or in your book, it's going to have minus, az times cosine of omega naught. And for the sine, you're going to have same denominator, z squared minus 2az cosine of omega naught plus a squared. And here it's just going to be a times z times the sine of omega naught, where omega naught, it's going to be the multiplier on n. And that's an a. Now, you have your book. If you look in your book on the actual Z-transform pairs, it's towards the end. How many see these two, if you've got your books? Y'all see them? Those crop up over and over again. And it's good to know these. And I'll tell you something else. This right here is something where you see it all the time. You may have something where a squared, you always look at the last singular value there. If you have 4, you know a's 2. 9, a's 3, so forth, right? 16, a's 4. Then this term, remember it's 2az, so if a was 2, and you had a number there like 5 or 4z, then the actual value, I mean, if that's, no, that would actually be the form right there. But the a is the thing that gives you this value right here. This coefficient will be twice a, and you get the value of a from that. Now, I'll spend some time. The upstairs thing right here, the thing that really determines the value of these things, I'm not saying this very well, but whenever you have something where, suppose this is 4, just listen to me now. Suppose this is 4, but the operator here, it's really this. It's 2a times the cosine. Suppose this is 0, that there isn't anything here. Understand? That means cosine of omega naught is 0. And that means the cosine is 0 of pi over 2, right? And yes, it's 0 again, and 3/2 pi. But always take the value, the positive value, that makes either the sine or cosine 0 in, I guess you could say in the first quadrant if possible, between 0 and pi. Don't add, don't add complexity unnecessary. And the best way for me to do a lot of these is just actually solve some problems applying them, and I'm going to. But you just understand these forms crop up over and over again. You have to know them, and you get used to using them. Now that I said that, and we use them for the inverse Z transform more than anything. So just listen to me on that one. All right, now, next thing. Got a lot of little notes about this. The next thing we're going to do is the inverse Z transform. Now, I'm going to tell you the easiest way to do it. I'm not going to give you a lot of stuff that he does and show you this method is sometimes used. No. Here's the easiest method and the most common method. It's just like when we did it with Laplace transforms and inverse Laplace. We do partial fraction expansion, and we recognize the common forms, right? Single poles, we knew with Laplace, went to e to the minus at kind of deal, u of t. Same thing here. Now watch this and please appreciate it. So I know that if I have, and I'm trying to do this, do it this way. If you have x of z, here's the easiest way to do it. Just listen. If you had x of z is something and you would like to get it of the form of a over z minus a plus b over z minus b and so forth, all right? The problem with that is all our transform pairings always have a z over z minus a. Follow me? So what we do is we divide this by z right off the bat. So you take x of z by z. And then you go out and you say I have a over z minus pole 1 plus b over z minus pole 2 and so forth plus c over z. And once you get the values of a, b, and c, then you multiply by z to get x of z. Now I'm going to demonstrate this so you appreciate it. Try to understand. I'm doing my best to communicate to you what I would want to hear from my prof if I was in your shoes. Because I know this stuff is troubling. You don't see any application. How are you going to design with it? Nothing's making sense. You will in time. You're just going to have to go with me and learn the basics first. You'll see how all this fits together and how important it is. So let's do an example of one.
Can we do it Wednesday?
What?
Or next class, sorry.
Class is over. Yeah, it's 1:51.
Well, no, you can't. You're going to stay. All right, I got you. All right, remember, Friday's quiz, Z transform.